Hi everyone. In this tutorial we're going to be talking about linear temporal logic and working through some basic proofs. Specifically we're going to be formalizing specifications. We're going to be checking the satisfaction of LTL formula with respect to particular models, and we're going to be doing some equivalence proofs. A quick note before I continue. In a lot of these proofs we'll be analyzing the semantics of particular formula. So we'll go from something like this, which this says that there's an infinite word sigma which satisfies phi or psi. And of course the way we interpret that in the semantics of LTL is that either sigma satisfies phi or sigma satisfies psi. When I go through a proof sort of a little bit more quickly, I'll say something like by the definition of satisfiability with respect to disjunction when I'm making the transition from this sentence to this sentence. But I'll usually just write something like this, right? So we go from this sentence, if and only if, and here's the semantic interpretation. And this indicates that we do this logical step according to the definition of satisfiability with respect to disjunction. Okay, so suppose we're reasoning about a system which can receive requests and send out answers. So in LTL, we're always talking about formulas with respect to a particular set of atomic propositions. So in this case, the sort of atomic behavior of our system is receiving requests and sending out answers. So it makes sense to let the set AP just equals these two propositions, rec and ands. These are atomic. The idea being that a state which is labeled by rec is a state at which the system receives a request, and a state labeled by ands is a state at which the system is issuing an answer. So here's an example of a very minimal transition system over this set of propositions. We have one initial state here called rec. Rec has one transition to wait, which has one transition to the state ands. This state ands has a transition to a state wait, which then loops on itself forever. Ands also has a transition to rec, and then rec and ands loop alternately on themselves forever. So in this instance, we'll define a particular labeling function from the set of states S to the power set over AP. So we'll define it as the label of a state wait is the empty set, and the label of any other set S, where S is not equal to wait, is just going to be the singleton set containing S. So in this instance, all of our labels are going to be singleton sets, but in general, it doesn't have to be. The label of a state could be any subset of the power set of, or any subset of the set AP, or any set in the power set of AP. But in this particular example, all of our sets are going to be singleton sets. And this is an example of the machine M1 from the previous slide, where we've just replaced all the names of states with the corresponding state labels. So you can see the two await states just became the empty set, and the other states just became the singleton sets containing the names of those states. So we'll see in a bit about forming words using that label. So say we want to formalize the property presented in English as no request is left unanswered. Now, of course, there's a number of ways you can do this. One way is to notice that the property basically is describing an invariant for our system. We have a particular local behavior that is a request always leading to an answer, and we want to make sure that this holds throughout the entirety of an execution of that system. So here, one strategy we can use is that we can define sort of the local behavior that we want, and then quantify it over the entire path. So for example, this is sort of the local behavior we're looking for, right? This is saying, okay, I see the label rec, and this implies that I'll eventually, right, see the label ands. And of course, if we want to quantify that over the entire path, we just wrap that whole thing in this always operator, right? Pretty straightforward. Recall from the lecture, the definition of LTL syntax only has as primitives the Boolean connectives of conjunction and negation. So we define, for instance, disjunction in terms of negation and conjunction. And then implication, as we see here, is defined in terms of negation and disjunction. So let's say for whatever reason you didn't come up with that last answer. Another way you can look at this sort of task of formalizing a natural language specification is to sort of break down the English or whatever language it's in and try to sort of work it into a way that's amenable to the kind of modalities that we use in LTL. So for example, when we look at the sentence, no request is left unanswered, well, we're actually saying that it is always the case that the system doesn't let a request go by without giving it an answer. All right? If we play with that a little bit, we can sort of come up with a sentence like, it is never the case that a request is made and an answer will never be issued, right? So you never have the case in the system where the system gets a request and then from that time onward, there's never any more answers, right? If you really are pedantic about it, you can turn this into, it is always not the case that, and then in brackets, a request is made and there is always not an answer, right? The always in the second case saying always from this time onward. And this, of course, is not really comfortable English, but this happens to be very amenable to our formal syntax. So here we can see that this is very easily translated into an LTL formula. And of course, this is exactly logically equivalent to the previous formulation we saw on the last slide. So if either of these approaches work for you, then they're logically equivalent. But of course, you always have to be careful when you're making these sort of formalizations because natural languages can be ambiguous. So you might want to try a couple of different ways that seem like they should be equivalent and then prove that they're equivalent to make sure that you have the right semantics. And we'll see how to do that in a bit. Okay, so let's go with the first formulation. We'll define a formula phi as always, and then in brackets, rec implies eventually ands. So the natural question we ask, and this is the fundamental question of model checking, is does M1 satisfy phi? Well, we know by definition M1 satisfies phi if and only if for every path pi in all the paths of M1, that pi satisfies phi, right? What does it mean for pi to satisfy phi? It means that the trace of pi satisfies phi. So this infinite word, right, the infinite string of labels on successive states in the path phi satisfy phi with respect to the semantics of LTL, right? And this is a question that we know how to answer. So looking at our particular M1, we have to figure out what all the paths are in M1, right? So in the first case, we have the path starting in rec, going to wait, going to ands, and then wait looping on itself forever. The other path you have is rec, going to wait, going to ands, and then rec and ands looping on themselves forever. Rec here is our only initial state. And so these are the only two infinite words that you can form using this transition system. These are the only infinite paths that you can form using this transition system. What we're really looking for are the infinite words, which are induced by the traces of these paths. So if we apply our labeling function, we find that the trace of pi1, which we call sigma1, is the singleton rec, or just rec, followed by the empty set, followed by ands, and then the empty set again for infinity. And the second word we get, sigma2, is the trace of pi2, is rec, followed by the empty set, followed by ands, and then rec and ands in alternation forever. All right, pretty straightforward. Like I said, in this case, all of our state labels are singleton sets, but they don't have to be in general. It all depends on how you define the labeling function. Okay, so does sigma 1 actually satisfy phi? Well, looking at the definition of phi is this always operator around this other formula. Now we know how to interpret an always formula with respect to satisfaction. And this just means that for any index I, sigma 1 at I satisfies whatever is inside the operator. In this case, it's this implication. So if we want to understand what this implication means, well, we said in a previous slide that implication was defined in terms of negation and disjunction. So let's just substitute that definition. Okay, that's just by the definition of implication. Now I want to get rid of this disjunction operator. And we know how to interpret disjunction with respect to the satisfaction relation. This is the equivalent sentence. It says for any I, either sigma 1 at I satisfies not rec, or sigma 1 at I satisfies eventually ands. So first let's take care of the negation, right? So now we have for any I, sigma 1 at I does not satisfy rec, or sigma 1 at I satisfies eventually ands. Now finally we'll interpret that eventually operator using the satisfaction relation. And this introduces a new quantifier. So our final sentence is, for any index I, either sigma 1 at I does not satisfy rec, or there exists some j greater than or equal to I such that sigma 1 at j satisfies ANDs, right? Notice here, when we unpack this modality operator, the always, we were starting at sigma 1 itself, whose first index is 0, right? And so we say for any I greater than or equal to 0. Here, we were unpacking this operator with respect to sigma 1 at I. So rather than saying for any j greater than or equal to 0, we have to understand that we're starting from the ith index in this word. So instead of saying there exists j greater than or equal to 0, we say there exists j greater than or equal to I, right? And this I is the same I that's bound by this quantifier, right? So let's make sure we keep track of that. Okay, so now that we understand what this actually means, now we just have to prove that this sentence actually does hold for the word sigma 1. So one thing you notice is that for any I greater than 0, strictly greater than 0, this first clause holds, right? This holds when you don't see rec at that particular set in the infinite word, right? So when I is equal to 0, this obviously shows us rec, so that doesn't work. But it works for 1, it works for 2, it works for 3, 4, 5, and all the rest. So for any I greater than 0, strictly greater than, the first case holds. Okay, so then we just have to worry about I is equal to 0. But when I is equal to 0, right, well, obviously we can't get this satisfied because it does satisfy rec. But we see that when the index is 2, or 2 greater than 0, it does satisfy ANDs. So when I is equal to 0, the second case does hold with j is equal to 2. So in this case, we've said that for any I, either equal to 0 or greater than 0, one of these two cases holds. And that's exactly what we need to prove for the satisfaction. So now we're done. Okay, the other word that we got from the transition system was sigma 2. So does this one satisfy phi? And so we're using the same semantic unfolding of phi, right? We have the same logical sentence. We just have a different word that we're reasoning about. Instead of sigma 1, it's sigma 2. So we'll do a proof by cases again, and this time we just have to be a bit more careful. Just like before, when I is equal to 0, the second case holds with j equal to 2, right? So when I is 0, this doesn't hold, but we can still get the ANDs with j equal to 2. Perfect. And also like before, when I is 1 or 2, the first case holds for the exact same reason. You don't get rec here, and you don't get rec here. So then you can rely on the first case. But what about for I greater than or equal to 3? So in other words, when I is showing us one of these, right? So if you think about it starting at 0 here, so 1, 2, 3, 4. So 4 is going to be rec, 5 is going to be ANDs. 6 is going to be rec again, 7 is going to be ANDs again, and so on and so forth. And what you end up seeing, of course, is that if I is odd, then you can use the second case by just taking the next state, right? So if I'm at a rec state or I is odd, I can get the AND satisfaction just by taking the next index. On the other case, if I is even, the first case holds, right? Because if I is 4 or 6 or 8, it's going to be showing me the AND set, and it won't be satisfying rec, right? So we've got the cases for I is less than 3, and then for all I greater than or equal to 3. So we've showed it for every I, and so the proof is done. Okay, what about a different model, this M2? So this is different than the one I showed before. We have a new transition we can do here. And of course the question is going to be, does this new M2 satisfy phi? And you should be able to see that it doesn't, but let's actually prove it. So notice that we can form this word that we didn't get from the previous system. So this word is rec, followed by ANDs, followed by rec, followed by an infinite amount of the empty set. So now if we try to prove this using this word sigma f, we run into a bit of trouble. this fails for I equals 2, and it's easy to see why. If I is equal to 2, well, 0, 1, 2. So here this does satisfy rec because it's at this index. So it can't be satisfying this clause. But there's also no index after this 2, this I equals 2, which shows us ands. The only ands we get is I equals to 1, and 1 is not greater than or equal to 2. So in this case, neither cases are met. So M2 does not satisfy this formula. We're working through some equivalence proofs in LTL. We define the equivalence of two formulas as follow. We say that phi and psi are equivalent if every model which satisfies phi also satisfies psi, and vice versa. So we define this relation using, or we denote this relation using the triple equal sign. And we define it in a set theoretic way by saying the set of infinite words satisfying phi is equal to the set of words satisfying psi. Of course, we define the equality of sets in turn as a mutual subset relation. So this only occurs if the set of words satisfying phi is a subset of the set of words satisfying psi, and the set of words satisfying psi is itself a subset of the set of words satisfying phi. And you can look at this in a little more detail and just say for every word sigma, sigma satisfies phi if and only if sigma satisfies psi. Okay, let's do some examples. We're going to prove the duality law for the next operator. This is in your textbook. For any LTL formula phi, we have not next phi is equivalent to next not phi. Okay, so suppose sigma is some infinite word over 2AP. Let's assume that it's in the first case, so assume that sigma satisfies not next phi. Looking at the definition of satisfaction with respect to negation, this just means that sigma does not satisfy next phi. The same thing with the next operator. This means that sigma from the first index does not satisfy phi. Okay, let's do the negation semantics the other way this time. So this means that sigma from the first index satisfies not phi, and then doing the same thing again with the next operator in the other direction. This means, or this is equivalent to sigma satisfying next not phi. So in this case, we were able to assume sigma satisfies the first formula, and then show that it's equivalent to sigma satisfying the next formula. Okay, so that proof's done. Okay, let's prove the expansion law for the eventually operator. This says for any phi, eventually phi is equivalent to phi or next eventually phi. Okay, so let's do this in both directions, right? Because it's kind of like a by implication. We'll assume that if sigma satisfies eventually phi, then sigma satisfies phi or next eventually phi, and then we'll do the reverse direction afterwards. Okay, so we need to show that if we assume sigma satisfies eventually phi, we can prove sigma satisfies phi or next eventually phi. Okay, let's take our premise here. We need to show that either sigma satisfies phi or sigma satisfies next eventually phi, right? That's how you prove disjunction like this. Okay, so looking at our premise, if we unfold the definition of satisfaction with respect to the eventually operator, we see that this is what our premise is actually saying. It says that there exists some I such that sigma I satisfies phi. So we know that some I exists. We don't know much about it. We know it's a natural number, and if it's a natural number, then it has to be either, 0, or it has to be the successor of some other natural number. Okay, so let's do our case analysis on whatever the structure of I is. In the first case, if I is 0, our premise reduces to just saying sigma of 0 satisfies phi, right? But this is just sigma is self-satisfying phi, which is one of the two disjunctions that we can prove, right? This is our simpler case here. So in this case, we're done. Now, if I is equal to j plus 1 for some j, well, let's look at what our premise now tells us. So now it says that there exists some j such that j plus 1 satisfies phi, right? We just substituted j plus 1 in for I in our premise, and then we just sort of tweak this, this existential quantifier to now quantify over J. So now, from our premise, we have sigma 1 plus J satisfies phi, right? But let's turn this into something a little bit more familiar. If sigma 1 plus J satisfies phi, well, this really means that take sigma, take the first index of sigma, and then take J after that, right? Which is the same thing, obviously, as taking sigma, taking the first index of sigma, and then taking J after that. So we can write it more conveniently in this form. And this looks a lot like our semantics of satisfaction with respect to the next operator, right? Okay, so this is saying that there exists some J such that sigma 1 plus J satisfies phi. If we write it in this manner, it's easy to see that these are equivalent because you're just taking the first index of sigma and then J indices after that, which is the same thing as taking J plus 1 indices of sigma. But this looks, so now we have this existential quantifier and this index J, and this looks like our definition of eventually. So let's do that substitution for the satisfaction relation. And now we can just do the satisfaction relation for the next operator. And this gives us exactly this second case that we could prove. So in this case, we've completed our case analysis on I, and the proof is done for the forward direction. For the reverse direction, we can assume that sigma satisfies phi or sigma, we can assume that sigma satisfies phi or next eventually phi, and then prove that sigma satisfies eventually phi. So remember from your logic courses that to show P or Q implies R, right, which is this disjunction that's in our premise, we need to show that both P implies R and Q implies R. So in other words, we have to do a case analysis on our premise, right? Show that if it's the case that sigma satisfies phi, we can prove our goal, and if it's the case that sigma satisfies next eventually phi, then we can prove our goal. Okay, so this is what our goal looks like. We have to basically construct some J such that sigma J satisfies phi. And we're going to know how to do that J based on the case analysis of our premise, right? So this is our premise. Either sigma satisfies phi or sigma satisfies next eventually phi, right? We just broke this disjunction into the two cases. If it's the first case and sigma satisfies phi, well, of course we can prove that sigma satisfies eventually phi, right? The J is just going to be 0, right? I can say that sigma satisfies eventually phi if sigma satisfies phi right now. So if it's the first case, we just use J equals 0, and we're done. If it's the other case, and this is going to look like the mirror image of our forward direction, of course, we can unwrap the satisfaction relation for the next operator. So now our premise is telling us that sigma 1 satisfies eventually phi. Doing the same thing with the eventually operator says that there exists some k such that sigma 1 and then k after that satisfies phi, right? And now, of course, we know how to construct our J. Our J is going to be just k plus 1, because that's telling us that the k plus 1 index of sigma satisfies phi. And then we're done. Okay, so now we're going to prove the expansion law for the always operator. Now this says that for any formula phi, we have always phi equivalent to phi and next always phi. Okay, let's start with the forward direction. If sigma satisfies always phi, then sigma satisfies phi and next always phi. Now recall we're proving a conjunction, so to show that our premise P implies Q and R, we need to show that both P implies Q and P implies R. So in other words, take our premise P, sigma satisfies always phi, and prove that both sigma satisfies phi and sigma satisfies next always phi. By the definition of satisfaction with respect to always, our premise becomes for any I, sigma I satisfies phi. This is really handy because in particular, sigma at 0 satisfies phi, but that's just sigma itself. And so in this case, the left conjunct, right, sigma satisfies phi, is proved trivially. Now for the other conjunct, Note that if you take our goal here, sigma satisfies always next phi, if we interpret this, interpret the semantics of this formula with respect to first the next operator and then the always operator, we end up with this, right? We have to prove for any j, sigma 1, and then j after that satisfies phi. But we can also use our premise for this, right? Just use the case where I is equal to j plus 1. So that's pretty easy. Okay, for the reverse direction, if sigma satisfies phi and next always phi, then sigma satisfies always phi. So we need to prove that for any I, sigma I satisfies phi. And by assumption, we have both sigma satisfies phi and sigma satisfies next always phi, right? We just broke up this conjunction in our premise. So our proof is going to say, like, okay, take any I and show that sigma I satisfies phi. We don't know much about I, aside from it's a natural number, and so we'll have to do the same case analysis that we did before. So either I is equal to 0 or I is equal to k sum plus 1 for some k. In the first case, our goal here just becomes sigma 0 satisfies phi, which is just sigma satisfying phi, and that's one of our assumptions, so that case is trivial. In the second case, we need to show that for any k, right, I is equal to k plus 1, so show that sigma k plus 1 satisfies phi. By assumption, we have sigma next always phi, and if we unfold the next operator, we get sigma at 1 satisfies always phi, and then we can take that universal quantifier, right? For any k, sigma 1, and then k after that satisfies phi. But of course, this is the same thing that we needed to prove, right? For any k, sigma k plus 1 satisfies phi. So now we're done. Okay, this is going to be the last proof of this tutorial. It's a little bit trickier, so if you found those proofs a little bit hard to work through, then maybe spend some more time on that. And if you're ready for something a little bit longer, this will be an interesting one. So we're going to prove the expansion law for the until operator. This says that for any formula phi and psi, phi until psi is equivalent to either psi or phi and next phi until psi. It's a bit of a mouthful. All right, let's start with the forward direction first. So our premise is sigma satisfies phi until psi. We need to prove this disjunction here. So recalling the semantics of the until operator, this tells us that our premise is that there exists some j such that sigma j satisfies psi, and for any I less than j, sigma I satisfies psi. Okay. Well, if we take our premise as given, we can form two premises just by breaking it up, right? Our first premise 1 is going to be that sigma j satisfies psi, and then the second one is this universal statement here. So we just broken up our premise into two statements. But what do we know about j? Well, we know that j is a natural number, so let's try our case analysis. Either j is equal to 0 or j is equal to k plus 1. So this is our goal we want to prove, right? So we have to show that either sigma satisfies psi or sigma satisfies phi and next phi until psi. Okay, so looking at our case analysis, if j is equal to 0, then the premise 1 of the previous slide then becomes just sigma 0 satisfies psi. Of course, this is enough to prove the goal because one of our options is to prove sigma satisfies psi, and we have that exactly here because sigma j satisfies psi. We are in the case j is equal to 0, so sigma 0 satisfies psi. So this is done. If j is equal to k plus 1, on the other hand, premise 2 becomes this sentence here. For any I, which is less than k plus 1, right, because j is equal to k plus 1, if I is less than k plus 1, sigma I satisfies phi. So notice that to finish this proof for this direction, we need to show that either sigma satisfies psi or sigma satisfies phi and at next phi until psi. So the only premise that we have which mentions psi is premise 1. But since we're on the case that j is equal to k plus 1, well, that doesn't tell us that psi is satisfied right now. So we don't really have anything to prove that clause. So we should really just focus on proving that sigma satisfies phi and next phi until psi. Okay, so if we're just taking this as our goal to be proved here, recall our premises. Substituted k plus 1 for j. Let's look. So to prove psi, well, we have a universal here, right? So no matter what k is, we're looking at I less than k plus 1. Now if we choose I is equal to 0, the least that k could be is 0, but 0 is still less than 0 plus 1. Okay, so this inequality holds. So sigma at 0 satisfies phi. And that's exactly what we need for this left conjunct here. So now we just need to prove that sigma satisfies next phi until psi. So if we unfold the next operator, we get sigma 1 satisfies phi until psi. And then unfolding the until operator, this is the statement that there exists n such that sigma 1 and then n after that satisfies psi. And for any m less than n, sigma 1 m satisfies phi. And we're actually just going to use k, right? K is the number in our case analysis of our j. And we're going to substitute k in for n here, right? So the left clause of our premise is okay, so the left clause that we're proving here, right, that sigma 1 k satisfies psi, is exactly our premise 1 from before, right, where we substituted k plus 1 in for j. Now to show the other one, we have take any m, which is less than k, right, because we substituted k in for n. And we need to show that sigma 1 m satisfies phi. So note that if m is less than k, it also holds that m plus 1 is less than k plus 1, right, since m is less than k. But m plus 1 less than k plus 1 was exactly the inequality in our second premise here, right? So for any m plus 1 less than k plus 1, sigma m plus 1 satisfies phi. So since we have that, we immediately have our second clause here, right? Sigma at m plus 1 satisfies phi. Okay, now I'll quickly sketch out the reverse direction. Take as your premise sigma satisfies psi or this conjunction and show that sigma satisfies phi until psi. So if you take your premise here, you need to show that by the semantics of the until operator, there exists some j such that sigma j satisfies psi, and for any I less than j, sigma I satisfies phi. So again, since our premise is a disjunction here, we'll do a case analysis on our premise. In the first case, if our premise is the sigma satisfies psi, just use j equal to 0, right? So then you just have to show sigma j satisfies psi or sigma 0 satisfies psi, which is our premise here, so that's done. And then here, for any I less than 0, sigma I satisfies phi. But note here, the indices are all natural numbers, and you can't have a natural number less than 0, right? 0 is the smallest natural number. And so this right-hand side just holds vacuously, right? And so the second case, where the premise is sigma satisfies this conjunction, the proof of that to get phi until psi, I'll leave as an exercise to check your comprehension. You should be able to look at the forward direction of this proof to get the idea.